There are two types of waves. For this class, it doesn't really matter. I don't get into the mechanics. But there's longitudinal, and I'm spelling horribly wrong. So there it is. Longitudinal. And there's transverse. We're going to be looking mostly at transverse. Even if it isn't transverse, we're going to pretend it is. So longitudinal is where we have compressions and rarefactions. This would be like sound. So sound is a longitudinal. So we have these compressions, areas where the molecules have been compressed. And then we have something known as a rarefaction. It's the opposite of a compression. Another way is you can do vertical lines to group it. We're for the most part not going to be worried about longitudinal. Everything can be represented by the transverse. Transverses are what we typically think of as waves. They're sinusoidal. They look like a sine curve. They have a crest. They have a trough. If we draw an imaginary midline through it, then the distance from this midline up to a crest is known as the amplitude. And likewise, if it's from the midline down to the bottom, that's also the amplitude. The thing about these two waves, where they mostly different is how the particles are moving. So in a longitudinal, the motion of the particles is parallel to the motion of the wave. In transverse, it's the opposite, it's perpendicular. The motion of the particles is perpendicular to the motion of the wave. Note, waves do not transport matter. They transport energy. So, if you have a perfect system, let's say you're fishing on a perfect lake with a perfect fishing pole with a perfect bobber, that bobber will never move laterally. It'll never drift. It'll never go anywhere. Even if a large boat were to go next to it and a wave were to start pushing on it, the bobber will only move vertically. That's how it should go. Note that because of gravity and other things, that's not the case. But if you were to look at every individual particle of a wave, so let's say we have a water wave, we have something floating in it. In a transverse wave, which a water wave is, the individual molecules are only vibrating up and down. Same thing for air. With air, any individual particle is only vibrating back and forth, but they reach the exact same point every time. They don't move anywhere. Now, the reason why this isn't perfect in real life is because what is this right here temporarily? Slope. A ramp. And if you have gravity and a rolling ball or something on a ramp, what's it going to do? It's going to slide down it. Now, as this wave progresses, it's going to eventually flip and do something like this. And even if the ball rolled a little to the right, what's going to happen now? It should roll back to where it started anyway. And so, even with this, overall, the net effect will be it hasn't really moved very much. It might move a little left to right. Unless you have something like wind resistance that prefers a certain direction. So let's say there's a mild wind blowing this way, so it's easier for this to go down. And on the way over here, the wind kind of picks it up and keeps it from going all the way back to the left. Overall, we get a net movement to the right, but that's F equals ma. A force acting on this, it should be moving anyway. The only major thing is the fact that this is a ramp. It's easier for something to roll down a ramp than it is to slide across a stationary thing. Another thing is water current. So there could be underwater water currents also pushing it in another way. So Sam Rayburn, for example, is connected to a river, which means there is some motion there. But we live in a perfect world when we do physics. So we're going to ignore the motion of wind and water currents. And I take that back. We are doing transverse and longitudinal. I'm looking at the test too to make sure I cover everything. So, we have a fancy equation. By the way, this equation is the only one in physics that I know of where they have a stupid notation for it in some areas. We will learn the wave equation as this. The speed of the wave is equal to the frequency of the wave times the wavelength. So this is speed or velocity of the wave, or wave speed. This is the frequency of the wave. And this is the wavelength, or the length of the wave. I never see it called the length of the wave. Let me see if I can find the horrible notation. Alright, do not write this down so you don't get confused. Let's see if I can find it. What do they use for velocity? They usually only use it for speed of light. So we'll do electromagnetism later, but the speed of light has a special constant. So this would be speed of light. Do not write this down. And then we have frequency times wavelength. This is how they write frequency. You might notice it looks slightly different. Let's see if I can draw this better. So it's the Greek letter nu. It looks like a V, which really confuses it because that's what we use velocity for. So if you get help online, you'll occasionally see frequency you can write this down. Frequency is occasionally written using the Greek variable nu. Which looks almost like a V. And when they print on computers, it looks exactly like the letter V. So let me, I always capitalize the names of Greek letters usually. It's so here's a Greek letter nu. Have I been writing it wrong? Because I don't hardly ever. There's two ways to write it too. No, that's Ida. That's what I was thinking of. So it's right after mu. I don't even see it. Oh, there it is. Where's it handwritten? Because I think I've been writing it wrong. Okay, I have been writing it wrong. It is more like that. I've been putting the tail wrong. Wrong. It isn't curved to the right. It curves upward. So, like that. This is how it looks like. But it looks very similar to the letter V. RU. But it does have a small, more pointy end. Which gets very confusing. So, to illustrate what a wavelength is, if we choose two identical points, so let's choose this point right here. Notice that it is sloping downward. So it's sloping downward at this point. If we were to draw an imaginary line going through this point, we're going to go into the next identical point. So here it would be sloping upward, but here is the next identical point. That would represent the length of the wave. So to illustrate it on a much bigger scale. So if we have midline, right here would be the wavelength. So the wavelength is the distance between two identical points. It's also the distance from crest to crest, or trough to trough. Even though I draw these as if they're one wave, we technically would say this is more than the one wave. It would be called a wave train, but I never use that terminology. If you want to count how many waves are in this one wave, it's just how many wavelengths there is. So let's do an example. Let's suppose we have a dock by the beach. And we have a water wave passing by it. I guess I should also give the definition of frequency. Frequency is a measure of how many oscillations or cycles that occur in a unit time. We've already done frequency before when we did rotation. It's usually measured in hertz, and a hertz is equivalent to the inverse of a second. 1 over a second, or s to the inverse. 1, s to the negative 1. So suppose that we count the number of crests that passes the first pair. We count that 5 crests pass by the first pair. How do you spell pair? It's P-E-I-R, or no, it's I-E. It's P-I. In 2 seconds. We measure the distance between 2 pairs to be 10 meters. And notice that that 2 crests are on each, and I should say not pier, it would be pillar, are on each pillar with exactly one crest in the middle. How fast is this waterway moving? So let's draw our 2 pairs. So we have a crest here touching it. We have another crest. And then we have another crest right here. And the distance from this crest to another crest is 10 meters. So how many waves are between here and here? Between here and this point. How many how many waves is this? So remember, when I say how many waves, is how many wavelengths. So from here to here, so going to the next identical point is one wave. Then from here to here. So that means that we have 10 meters per wave. I prefer 2 waves. So this tells us that the wavelength is equal to 5 meters. By the way, do you know what this letter is? Yeah, but do you know what letter it is? It's the Greek letter lambda. If you can't draw it correctly, you can do this. You can make straight lines. It's lambda. Greek letter L. So lambda, our wavelength is 5 meters. We count that 5 crests pass by the first pillar in 2 seconds. So what is the wavelength? And what is the frequency? Yes. So frequency is per second, so there's 5 crests per 2 seconds. So crest is a fictitious unit. So this is equal to 2.5 per seconds, right? So this is equal to 2.5 hertz. So that's our frequency. Make sense? So the speed of the wave would be equal to its frequency times its wavelength. So that'd be 2.5 hertz times 5 meters. Which would give us a speed of 12.5 meters per second. Or hertz times meters, or meters hertz. A meter hertz, remember that hertz is really a per second, so that's the same thing as meters per seconds, or this. So that means that a crest, that means each crest is moving towards you at 12.5 meters per second. So let's do another. Oh, do you have the homework?
Still in my account.
Can you get it to me? So let's do some more examples. Let's suppose. Oh, let's do a famous example. So for electromagnetic waves, we'll go into this more later. The speed in a vacuum is, let me look up the precise value, is exactly, this is an exact number, 299,792,458 meters per second. We have defined meters and seconds so that this number is exact. It is approximate, and this is what we'll use. We'll use the approximate value, is approximately 3 times 10 to the 8 meters per second. So we will use this value. It's also 186,000 miles per second. So, in a microwave, oven, it produces microwaves with a frequency of 2.45 gigahertz. So the frequency is 2.45 gigahertz. What would this number be in scientific notation? So kilo is 10 to the 3. Mega is 10 to the 6. Giga would be 10 to the 9. So 10 to the 9 hertz. So that's the frequency. What would be the wavelength? Oh, by the way, we let the letter C represent this number as a constant. So, for EM waves in a vacuum or in air, light doesn't slow down that much, so it's approximately still C. The equation becomes the speed of light. So, speed of light is equal to the frequency of light times the wavelength of light. So if we're trying to solve for wavelength, wavelength would equal C over F. C is 3 times 10 to the 8 meters per second. And the frequency is 2.45 times 10 to the 9 hertz. This per second and hertz is just a per second, so per second and per second cancel each other out, giving us just meters. And this should be 12.2 centimeters. So this is 0.12245 meters, which is equal to 12.245 centimeters. So about, it's really 2.4 if you round it, because this is really 4.8. But this is something we can measure. We'll go into a lab and actually measure this. Have you ever used a microwave that doesn't have a rotating table, a turntable? So, growing up, that's the microwave we had. In which case, how you cook food is you look at the box and see what the recommended time was. So let's say it's a hot pocket and it says 2 minutes. You run your food for 30 seconds, and then you randomly move it to a different spot. Run it for another 30 seconds, randomly move it to another spot, and you repeat and repeat until you reach the time. And then when you eat the Hot Pocket, you pray that you were random enough to cook it. So I will actually draw the actual size of a microwave. So this will be to scale. So this is a 1-to-1 ratio of a microwave. So 12 1/4. And then what's half of that? 6 1/8. And then 6 1/8. So that is the size of a microwave in your oven. And it hits the side of the wall, and we'll learn about this later on. It'll reflect off the wall and produce something known as a standing wave. So it's constantly bouncing forth. These points right here, you'll notice is the node. So this is a standing wave. This would be a node. This would be the antinode. And let me just show you a video of a standing wave. So we'll learn about superposition later. What's happening is the microwave is constantly generating waves to the right. They're constantly hitting the other side and bouncing off them to go backward. So this won't be going backward. And the two waves will combine to make one wave.
Here it's moving. So the node is not moving. Here it's moving up and down, and here it's moving. So the node is not.
So all this setup is right here as a piston moving up and down at a certain frequency. And he has the right side completely stationary. So it's hitting this pole and then reflecting backward. So he's constantly sending waves to the right, but they're hitting a wall and they're bouncing backwards to the left. Obviously, a string can't be in two places at once. So this forward moving wave and this backward moving wave combine to give a single wave. And this is what it looks like. It's called a standing wave because it looks like the wave is standing still.
And here it's moving up and down. And we'll see that in a second with the high-speed camera.
So it's going to show you in high speed. So in high speed, even though you see it vibrating, it's still a wave that looks that's moving. This is called constructive interference. And we see this note right here is not moving very much.
Second harmonic. It's the second possibility for a standing wave through the calculations.
So here he's increased it up to higher dimensions. You can notice the antinodes vibrating quite a lot, and the nodes don't very move. Let me show you the. So this is it in slow motion. Even though it looks like it's kind of oscillating and staying still, in slow motion you can see that the waves are moving up and down. My point of introducing this earlier is to explain that we're going to get either, there's two ways of measuring it, depending on the microwave. But you'll notice that if it produces a standing wave your food is really only cooked right here. And a little bit of it's cooked right here and here, and almost none is cooked. So in between these two regions is where your food is mostly cooked. Right here is receiving no radiation, but in these two regions, barely receiving any. So what this means is if you put something in the microwave and it stands perfectly still and doesn't move, you're going to get boiling hot lava right here. So lava. And you're going to still have ice right here. So back in the day, when you cooked a Hot Pocket, it's always a fun game. Are you going to get a second or third degree burn on your lip? Or are you going to chip a tooth what's crunching on the ice? Always an exciting game to play. Especially if you're really hungry and you want to eat quickly. The best thing to do is, remember when we did heat? Things will eventually radiate heat wayward. So after 30 seconds, this heat is going to flow into these regions and warm it up. But if you were to position it so one spot is constantly receiving the radiation, it'll get super hot. And if one spot never receives any radiation, it'll stay frozen. Which means you should wait a little bit so that the heat has time to dissipate. Actually, that's still true with round table or turntables in them too. You'll notice everything you microwave will always have the words, "Wait a minute or two." That is because there is a chance some region of it got super, super hot, while another is super cold, and it wants to give you some time to move for the heat to dissipate over. Another thing, and this is going more into chemistry, ice doesn't absorb electromagnetic waves that much. So, but water absorbs them the most. What's going on here, if we look at the structure of water, these two hydrogen molecules can vibrate back and forth. And what is temperature? Temperature is average kinetic energy. And kinetic energy is the motion, so how much they're moving. So if we come in here with a microwave and hit this, think about a swing set. So we have this swing set. And let's say that we push this person. When do you want to push again? So this person is going to swing this way, and he's going to swing back. And when you get right back at you, you're going to push it again. And what's going to happen? The person's going to go higher. He's going to swing back, and if you wait to the very perfect moment that he's at the deal and you hit him again, you can make him swing faster. Microwaves are tuned to the natural resonant frequency of water. They're not tuned exactly. We want it to be off. We want the microwave to occasionally slow the water molecule down. Do you know why? Let's imagine we have a steak, and we have a tiny moisture of water here. If the top layer of water is constantly heating up and absorbing all the radiation, what happens to the inside of the steak versus the top layer? It will burn and start boiling the water while the inside stays frozen. Do you know how we gotten the coldest temperatures in the universe? Using lasers. So molecules constantly vibrating back and forth and moving around. If it's moving toward the laser, we shine a light on it and hit it. This will either do one of two things. It'll either slow its speed down, or it'll cause it to flip in the other direction. And then if it's moving in the other direction, we hit it from a laser here, and occasionally we can get to stop. Almost stop. So if it was perfectly tuned to water, the outside surface would absorb all the energy and get hotter and hotter and hotter, while the inside doesn't ever get hot. We want enough of the radiation to somehow miss the outer layer and hit the inside and warm those up. So it's not exactly tuned to the swinging motion of these hydrogens. It's done off-center, so that 60% of the time, I'm making these numbers up, it gets hotter, and 40% of the time, it gets colder. This enables you to cook the inside of your food because it's not perfectly tuned. If it was perfectly tuned, it would only heat the outside of your food. This is also why we have a defrost setting too, because it's tuned to liquid water, not ice. Ice already doesn't have, because the hydrogens are bonded in a crystal structure, they can't vibrate that much. This is why you have a defrost setting on your microwave, so that the moment the ice melts, it can begin absorbing the EM waves better. In which case, they'll heat up and quickly melt the surrounding ice as the heat is transferred to it. But that's why if you place anything frozen, it's preferred if you defrost it and let it melt first instead of trying to cook it. Because once it turns into water, the water is going to get hot very, very fast, while the ice doesn't. But we'll look at more examples tomorrow.